My name is Catherine Morris, and I'm from the University of Charleston in Charleston, West Virginia. And I'm going to discuss the impacts of Microstegium vimineum on native species. So all over the world, ecosystems are challenged by invasive species, and West Virginia is one of those areas subject to these pests. So I'm going to discuss how Microstegium vimineum affects the population of native species and how it grows in different habitats. So whenever we think about invasive species, we often think about these species as having explosive dispersal, few predators. They also threaten native species and are adaptable to different environments. So this is the driving force behind doing research on non-native species. So Microstegium vimineum is a shade-tolerant invasive grass that was originally used as package filling from China, and it was first found in the United States and Tennessee in 1919. Since then, it has spread to 14 other states in the U.S. It can alter soil pH and nutrients. So Warren et al. Found a correlation between Japanese stiltgrass and the availability of nitrogen. So they suggested that this may trigger the plant to produce more nitrogen and alter the soil biochemistry. So this is a problem in West Virginia for those who want to forage or use native species commercially. So Microstegium vimineum is usually found in a disturbed location. So this could be a roadside, a public trail, or maybe a floodplain. And like I said before, it's shade tolerant, so it only needs 20% ambient light to survive. And Cole and Wilson did a study, and they found that canopy openness and biomass of other species were significant in determining the production of Japanese stiltgrass. So they found a negative relationship between Microstegium vimineum and biomass of other species. They also found that as canopy openness increased, so did the production of Japanese stiltgrass. Oswald et al. Also found that Microstegium vimineum responded positively to canopy disturbance. So they opened up the canopy to see how Japanese stiltgrass would respond, and it responded positively and it grew more. And in turn, this decreased the diversity of native species and also native species richness. So Microstegium vimineum has a negative impact on the richness of native species, but its effects take hold later in the growing season when the grass has matured more. So Adams and Engelhardt experienced a decrease in species richness in invaded plots in the second and third months of their study. Florian Clay also did a similar study looking at invaded plots from Japanese stiltgrass, and they observed a 19% decline in species richness in the second year of their study and a 43% decline in species richness in the third growing season. So as native plant biomass decreases, it just allows more room and more resources for the invader to take over. So I wanted to see the relationship between stem count of Japanese stiltgrass and native species, and I also wanted to see how it grew in different habitats. I also wanted to see how canopy openness affected the growth of Japanese stiltgrass. So this was a preliminary study just to get a general idea of these relationships. So I thought that the public trail would have the highest stem count because it was mostly disturbed by humans. So it was a heavily trafficked trail. And then I also thought that the stem count of Japanese stiltgrass would increase as canopy openness also increased. And then I also thought that as stem count of Japanese stiltgrass increased, the native species stem count would decrease. So I chose 3 locations. I chose a field, part of the interior forest, and a public trail. The interior forest and the public trail were both taken in Fayetteville, West Virginia. The public trail samples were taken adjacent to the Nodelberg Mine Trail, and then the interior forest samples were taken 30 meters off the Timber Ridge Trail. And this was a brushy, overgrown area where it didn't look like a lot of hikers had been through. And then the field location was taken in South Charleston, West Virginia, about 20 meters off of the Little Creek Park Trail. And this area had 30% or less canopy cover. And it was an unkept area, kind of overgrown as well. So what I did is I had a 1/2 meter by 1/2 meter PVC pipe square, and I randomly tossed it in the direction of where Japanese stiltgrass would be. So then I counted the stems of Japanese stiltgrass, I counted the native species stems, and then I also took a photo of the native species so I could identify them later, and I took a photo of the area above the plot so I could measure canopy cover. I took 10 samples per location. So if we zoom in here, we can look at these graphs a little bit better. And here we have average stem count per location. And the interior forest had the highest average stem count, which I did not expect, although it is just a little bit higher than the public trail. And I did an ANOVA, and I got a value of 0.277, so the stem count did not differ among the 3 locations very much. So then I also measured average species richness per location, and I found that the interior forest had the lowest average species richness, and the public trail had the highest. Once again, I did an ANOVA and got a 0.323. So there was some homogeneity among these values. Then I also had average percent canopy cover, and the interior forest had the highest average percent canopy cover, and the field had the lowest with 30% or less. And I first did a Levine's, and I got a p-value of 0.467, so then I went on to do a Kruskal-Wallis, and I got a value of less than 0.001. So then I also wanted to see the relationship between stem count and species richness, of course. And so I did a Spearman's rank, and I got a value of negative 0.309 and a value of 0.048. So we see a little bit of a negative correlation here between stem count and species richness. So then I also did a conical correspondence analysis. And what this does is it defines the relationship between plant species and environmental variables. And my environmental variables were stem count of Japanese siltgrass and percent canopy cover. And looking at this graph, we have the field samples clustering in quadrant 1, the interior forest samples clustering over quadrant 3 and 4, and then the public trail clustering over quadrant 3. So we did see that the stem count of invasive species and percent canopy cover are associated with plant communities in the public trail location and the interior forest location. So we also did a Pillai's trace, and we got a p-value of 0.015, and that just shows the fitness of the test. So we also did a Shannon's diversity index, and this just measures the abundance and evenness of species per plot. So normally you get a value between 1.5 and 3.5. And for the field, I got a 1.5. For the interior forest, I got the lowest at a 1.47. And for the public trail, I got a 1.6. So to make some comparisons here, I hypothesized that the area with the highest stem count would have the lowest species richness, and that was true in this case. So the interior forest had the highest average stem count, and it also had the lowest species richness, and interestingly enough, it also had the lowest diversity at 1.47. But I did expect the public trail, which was more disturbed and a pretty heavily trafficked trail by humans, to have the highest average stem count. Although it wasn't far past the interior forest could have been a little more disturbed by bears or foxes or other small animals. So I made these hypotheses after looking at Nord's studies, and she was looking at Japanese siltgrass in different locations in different areas, and she found more stems of Japanese siltgrass on a roadside location than the interior forest, possibly because the seeds are spread by cars along the roadside. So I also hypothesized that as canopy openness increased, so would the Japanese siltgrass stem count. And this was not true in this case because we had a low canopy cover here and also the lowest average stem count. So this could mean that in these locations, like the interior forest, the Japanese siltgrass was just able to take advantage of the intervals of high sunlight that it did get. This area, I do believe, is in need of further research. So if I was going to take this research further, which I hope to do in the future, I would want to expand this study throughout West Virginia more. And I would like to look at a few different habitats in West Virginia, and I would like to have 5 to 7 trail locations, 5 to 7 interior forest locations, and 5 to 7 field locations. So I would want to measure percent canopy cover again, look at the native species, and look at the diversity. I would also want to have 15 to 20 samples per location. So then I think it would be interesting to also measure the elevation. So I would want to vary where my samples are throughout West Virginia. So I'd want to take some possibly at Spruce Knob and possibly at lower elevations just to see how that might affect the Japanese stiltgrass growth. So I would also measure canopy cover similar to how I did before. And then I want to categorize the data based on the amount of Japanese stiltgrass. So then we can kind of, if there's a lot of stems, we might see less native species, and we can kind of compare those. So I think that making these specific guidelines for furthering this research would give us more specific results. As in here, we just have general results of the relationships that we could see. So I think furthering the study, we'd be able to see how it affects West Virginia and also how it affects native species more specifically. Thank you for listening, and if you have any questions, my information will be below.